through it quickly. So here we go. 12.2 techniques of evaluating limits. Remember, we don't have time for you to write down all the little things, so you'll come back to it. These are our goals of what we're going to learn. We talked about the dividing out technique. How do you know when you should divide out? So the functions, that means that you're going to find a common factor, divide it out, and then that allows us to use direct substitution, okay? How do we know we want to do this? We talked about it yesterday. It's if I initially plug in the value and it creates a 0 in the numerator and a 0 in the denominator, we call that the indeterminate form, okay? So whenever it creates me going straight into direct and plugging it in, if I have a 0 in the numerator and a 0 in the denominator, that's called the indeterminate form, okay? That means that there's a common factor between our numerator and our denominator, and our job is to find that common factor, okay? So indeterminate form leads us to, now we're going to divide out. So this is just a summary of all of that. So then we did this. So then we went ahead and divided out. So on our example that we did together, we did example 1 together, and we realized that we got indeterminate form, right? 0 over 0. So that told us we needed to factor and divide out. So we factored, divided out x minus 3, and then we were able to take the limit after doing that. Yes? Everyone remembers that? Okay, cool. Now, we're on to the rationalizing technique, which is where I think we stopped at in this class. Rationalizing technique is going to be used when you are going to try to rationalize the numerator, because in its current state, it creates an indeterminate form. So rationalizing technique means that you're going to multiply the numerator and denominator by the conjugate of the numerator, okay? The first time we really talked about conjugates was when we talked about complex numbers. So for example, here we have a plus bi, and its conjugate would be a minus bi. The conjugate is the opposite operation, okay? The opposite binomial operation. So what, for example here, if I had the square root of x plus 4, its conjugate is going to be the square root minus 4, right? That still applies even if it's not just complex numbers, all right? How does that help us? Well, here we go. So if you look right here, this is like not on your paper, but you can add it if you want. I was trying to save space. So practice that we have up here is we have the limit as x goes to 0. If I was just to do direct substitution and plug in 0, notice how it ended up in the indeterminate form. Do we see that? 0 over 0. All right, well, what does that mean? Well, it means that sum's not going to work in this form. So what can I do? Well, this is where you're going to rationalize the numerator, okay? So when we are rationalizing, that means that we're going to multiply the numerator and the denominator by the conjugate of the numerator. So notice here it was square root of x plus 1 minus 1. Its conjugate is going to become the square root of x plus 1 plus 1, okay?
Wait, why? Wait.
You rationalize the numerator.
You only do rationalizing like.
When you end up with the indeterminate form.
Oh, I thought you said that we do that for.
What do you do if there's 3 terms? I think it's not just 2.
Then you can't rationalize.
Okay.
Yeah. Okay. All right. So to rationalize, we're going to distribute using FOIL. And when we distribute using FOIL, it's going to cancel out the middle term and it sets the root free. Yes.
If there's just 1 term, do you like change the sign?
Yes. Okay. So after we do that, we're going to be left with x plus 1 minus 1. And what happens to our 1s? They cancel out because one is positive and the other is negative. So then all you're left with is now x over x times the square root of x plus 1 plus 1. And your x's are going to cancel out. Now in my current form, could I plug in 0 and get a value?
Can you say the question again?
Now in the current form, after I rationalize, can I plug in 0 using direct substitution and get a value?
Yes. Oh, yes.
Yes.
It's just 1.
Exactly. I can now just plug in 0 and get a value. So that's what we're going to do now because we're good enough. After we divide out the common factor, we're now going to plug in. No, I just told you. I just said I didn't put it on your notes. You're going to have to save paper. It was too much. Yeah. And now I can plug it in. So I'm going to plug in 0. So these are equal, but this is just rationalized. So this was our original, right? And now here, this is where we're at. Okay. Now I'm going to plug in 0. So I'm going to use direct substitution, plug in 0. When I plug in 0, it becomes 0 plus 1, which gives me 1, and the square root of 1 is 1. So we have 1 over 1 plus 1, which makes our limit 1/2.
Yes, Alexis.
So that is the purpose of rationalizing so that I can have,
So with rationalizing, we only make everything positive, we don't make a negative, or do we switch it?
it depends. So if it started off as a subtraction, then it becomes a positive. If it starts off as a positive, it becomes a,
And we only change we don't change the first set of terms, we change the ones that are like separate terms fully, like we don't change the one within the rest.
yes, because this is one term. Yeah, exactly.
Okay.
Yes. All right. Next part is using technology. Now, when everything else fails you, so like you can't factor out, you can't divide out, you can't rationalize, your next best hope is technology. Okay. So using technology to look at the graph or the table and analyzing from that. That's literally what this whole sentence is saying. Use the graph and table to analyze. Okay. So that means dividing out didn't help us, rationalize didn't help us. So what can we do? Well, here we go. We're gonna be analytical about it. So if I have the limit as x goes to infinity, x goes to 0 of 1 plus x to the 1 over x power, I can't really do anything here, right? I have a 0 in the denominator of a power. That's not going to do anything, and I can't rationalize. I can't do nothing. So I'm going to go to the calculator. I'm going to put this in as a function. So I'm going to put f of x in, and I'm going to go look at the table, or I'm going to go look at the graph. In this case, I always start with the table because sometimes it's easier to see a pattern from a table than a graph, in my opinion. So what did I do? I went to the table. And when I went and looked at the table, I saw that coming from the left and coming from the right, approaching 0, there's an error, right? And so I'm approaching 0, coming from both sides, there's going to be an error. And that error is my value, right? I have an undefined value, but does that mean I don't have a limit? No, your value and your limit are not necessarily the same thing. Okay, so to approximate my limit, I'm going to take the average of those values. The other thing I want to take note of is look how close I got to 0. Do y'all see? I didn't just go 1, -1, and 1. I changed my scale to be as close as possible to 0, right? So that I could see, okay, what's really happening? Well, it's getting closer and closer and closer. So I'm going to find the average of these two. And when I find the average of 2.7196 plus 2.7196, what do I end up with? I end up with 2.71825. So my approximate limit is at this. Okay. This function, if you remember from exponentials in Algebra 2, is actually your E. That's the value of E. So this is actually the formula used to approximate the value of E. And that's where that comes from. But it is a formula we've seen before, and we've talked about it before when we talked about exponential functions and natural log and the value of E in the past. E is just a value. Remember, we talked about this. E is like pi. It's a number that goes on and on and on.
But it's not always 2.718.
Yeah, so this is saying that this is what this formula is. It's approximating the value of E. So this right here is what E is worth. It's almost E, exactly.
E is always going to be the 2 point whatever.
E is always 2.718. Like pi is always 3.145, right? All right. One-sided limits. So one-sided limits we talked about. You can look at a limit from the left and from the right side. So this was what should have been written down. So there's a space that says one-sided limit. This is what goes in that space on your notes. Okay. A one-sided limit means that you no longer just have the values. You're going to have a minus. So you'll have a limit as x goes to the left, which is what that minus means. And this is saying the limit as x goes to the right, which is what that plus means. Because to the left are our negative infinity and to the right is our positive infinity. Yes.
So if it says x goes to c negative, are you going from positive?
From the left. I'm sorry. I didn't say go. So you're going from the left.
Three
So
negatives.
you're starting negative.
You're starting at negative and working your way.
It's x is c negative. That means it's starting.
You're going
from
like
the
this.
left side. Okay.
Yeah. And if it's C positive, you're going.
So C negative is a positive graph.
Doesn't have to be. No, it's just the direction you're heading in.
Okay.
Yeah,
So it's heading right. It's just right.
exactly. All right, so let's look at an example of how this may look. So here's a practice problem. We have f of x equals the absolute value of 2x divided by x, okay? Absolute value in itself is gonna tell us that we're gonna have two parts of a function. Does that make sense? And so when we graph it, it looks like this. Okay, so if I ask you, what is the limit of this graph? 0 minus or 0 negative, what would that be? What would be 0 negative?
Your negative would be -2.
-2. That's coming from the left. Where am I heading at, right? So therefore, the limit of 0 plus would be 2. Huh?
So it's C is a C. Oh, 0 is just a C.
Yes.
Okay.
0 is your C. So do we see why that is? So here, coming from the left, I'm heading to -2, but coming from the right, I'm heading to +2, right?
So if there's no sign on it, they're just coming to look right.
Yes, and then that's just asking for the general limit, okay? Yes. Mhm. So the general limit here, does it exist?
No.
No, in order to have a general limit, your left and your right side have to be approaching the same. And are our left and our right approaching the same? No, one's approaching -2 and the other's approaching 2. So the limit does not exist for this because they are not equal. Make sense? Yeah,
Does not do the limit situation.
you have a limit coming from the left and you have a limit coming from the right, but the limit of this function does not exist. Because your left and your right are not approaching the same value. Okay, yes.
If, at 0, if it was like the same, but at 0, it equaled 2, like it still comes towards -2 and then it still goes to 2, but it equals 2.
That's your value,
with
not
the
your limit.
So there still would be no limit.
There will still not be a limit, but there will be a value at 0. Yes. He said if it's a closed circle at 2, 0, 2, if it's a closed circle, that means there's a value at 0, but there's no limit at 0 because they're still not approaching the same thing. Okay. All right. So again, if your left and your right are doing different things, you automatically do not have a limit. Does that make sense? All right. Next part is limit from a calculus view. Okay. Limit from calculus. We use what's called the difference quotient. So in order to start off understanding what the limit is and approximating the limit, we use what's called the difference quotient. Okay. This is your difference quotient. Your difference quotient is the limit as h goes to 0. And there's two parts. You first are going to find f of x plus h. And then you're going to plug it into this limit. And then you just simplify. You just got to simplify, simplify, simplify. Okay. This right here, if you do direct substitution into the difference quotient without simplifying, it's going to always produce an indeterminate form. You have to go through and simplify. Otherwise, you're going to always get indeterminate form. And you're like, it didn't work. It doesn't exist. No, you just didn't simplify. Okay. So you need to go through and simplify. All right. Is there room at the bottom of your page? Like underneath this? Like after you write the rule, did y'all write this down? Sorry. You need to write the,
Oh, yeah, we've written that down.
yeah.
Written that down.
So you should have written down the difference quotient. The limit as h goes to 0 of f of x plus h minus f of x divided by h.
It always goes to 0 for h.
H always goes to 0 in the limit, in the difference quotient. Oh, no. So I'm going to do a practice one. And then after I do the practice one, there's going to be the example one that I want you to try.
Like in this box thing.
Yeah. Don't you have space for an example one?
Yeah.
Well, I don't know why there's graphs there, by the way.
Right.
Little graphs. They're on all of them, in case you want to graph something.
Ooh.
All right. So for example, here we have, if I have f of x equals x squared minus 1, the first thing I'm going to do is take x squared minus 1 and I'm going to plug in. Why did I do 3? Oh, because I think I just did. I don't know why. I was just doing it at a constant. I was like, wait, why did I write x squared minus 1? It's just f of x equals 3. It's just a constant line. So if I'm at f of x equals 3, this is a constant, right? So when I plug it in, I'm going to have 3 plus h, because that's my x. I'm going to have f of 3. All I'm doing is plugging it in, and I'm going to go through and evaluate it from there. So what f in the beginning? My x value is 3.
Oh,
It's
that's
x plus
it.
h. Yeah. So at 3, what's happening? So then I'm going to go through and evaluate it using direct substitution. I can't yet. So I'm going to go through and simplify it. I don't know what I did here. I feel like I missed something.
Find the square.
I don't know.
Wait, I think it's.
I don't know what I was
X
thinking when I made
equals
this problem.
X squared minus 1 at 3.
I think I forgot something in my notes.
I think it's at 0.3.
Fine. Oh, I didn't write my point at x equals 3. That's what it is. I didn't write at x equals 3. Thank you. Find at x equals 3. There we go. I was like, something's missing and I have no clue what. Yay, notes at midnight. There we go. Sorry, that little, perhaps you may need that. So therefore, when I plug into the rule here, I'm going to plug in for wherever there is x, I put in 3. So in here, it's f of x plus h minus f of x, right? But what is my x value? 3. So I plug 3 in, check. And I'm just going to go through and I can simplify it by finding each piece. So I'm substituting 3 plus h into this formula. So where x is, it becomes 3 plus h. Do you see that? So this is 3 plus h squared minus 1. And this is going to be 3 squared minus 1. Here, all I'm doing is foiling and combining like terms, right? So I FOIL, combine like terms, and I get 9 plus 6h minus h squared. Over here, I'm going to clean this up. 9 squared minus 1. I went ahead and distribute here just because I want to make sure I understand. When you have a minus outside of parentheses, that applies to everything inside, not just the first term. So it makes my 9 negative, but it turns something that's negative into a positive. And now at this point, you're going to combine and eliminate. So what I can eliminate is 9 and 9, negative 1 and 1, and they go away. Do we see that? So after I eliminate, all I'm left with is 6h plus h squared. What can I do here?
Oh, it's h squared over h, you can divide it into 6.
Exactly. I can divide out an h. Do we see that? I can divide out an h. So I can divide out an h, because if not, it's going to be indeterminate, right? But I can divide out an h. And when I divide out the h, I'm going to be left with just 6 plus h.
Yes.
Can I find the limit now?
No.
Yes. So at x equals 3 for x squared minus 1, the limit is 6.
How did we get 6 plus h? Can you go back to the?
Yes, I
slide?
can.
We took out the h.
We factor out the h.
Oh.
And what happens here?
Oh, okay.
They cancel out, and all you're left with is 6 plus h. So here, sorry, the limit would be 6.
Theoretically, could you just like put sorry, more theoretically, you just put it in the calculator, and it would tell you.
The limit, that calculator won't tell you the limit. You'd have to put a program in.
Back a little bit.
Yes. All right, so the one in your notes, your example 2, you have 9 minus 2x squared, and I want you to find the value of x at 3 for that one. So on your paper, you have example 2, right? At 9 minus x squared, f of x equals 9 minus x squared, and I want you to find
It's on,
at x equals 3.
where the graphs are.
At the graph, do y'all not have it?
Where it says the derivative of.
X equals 9 minus 2x squared.
9 minus 2x squared.
Oh,
Oh, I'm on the wrong side.
there's no example.
Oh, I didn't have an example. Okay, we're on the other side. I thought I gave y'all an example. My bad, guys. I didn't give you one to do on your own. I failed.